Hello everyone, welcome back to the lecture session on infinite series. In the past two lecture sessions, we have defined infinite series and we have seen the very important concept of convergence or divergence of an infinite series. Now, today's session, we will continue with this topic and we will see some tests of convergence for positive series. That means we are now going to deal only with series for which all the terms are positive. And why do we need such tests of convergence? Actually, earlier we had been examining a positive series for convergence or divergence character using the definition where we used to first construct the sequence of its partial sums and then test whether that sequence is convergent or not. And depending on that, we come to a conclusion about the given series. But these tests of convergence will actually help us to examine the convergence condition of a series directly without constructing its sequence of partial sums. So let us start, and today we will see the comparison test. This test again has a number of forms. So first we see the comparison test 1. If sigma un and sigma vn be two series of positive terms such that un is less or equal to vn for all values of n, then the series sigma un converges if the series sigma vn converges. So what we are doing essentially is we compare the terms of the two sequence for each n, and we see that if it happens that un is less or equal to bn, then obviously this sigma vn is the bigger series. And therefore, if the bigger series converges, or in other words, it has a finite sum, it's obvious that the smaller series will also have a finite sum and therefore it will converge. We have a similar result for divergent series. So now suppose that if sigma un and sigma vn be two series of positive terms such that un is greater or equal to vn for all values of n, then the series sigma un diverges if the series sigma vn diverges. So what is happening over here? Again, we are comparing the terms of the two series. Now, but here un is greater or equal to vn. So that means sigma un is the bigger series and sigma vn is the smaller series. So if the smaller series diverges, again it's obvious that if the smaller sum is infinite, then the bigger sum will be also infinite and therefore sigma un will diverge. Next, we will see again comparison test but in a different form, now in limit form. So if sigma un and sigma vn be two series of positive terms such that limit un by vn as n tends to infinity equal to L, where L is a finite number, then the series sigma un converges if the series sigma vn converges. So if we compare the two terms in the limit form and if that limit is a finite number, then if the second series converges, then the first also converges. The next one, if sigma un and sigma vn be two series of positive terms such that again limit n tends to infinity un by vn equal to L, where L is now a non-zero number, so it cannot be zero, but L may be infinite. In that case, the series sigma un diverges if the series sigma vn diverges. Now we will see some examples to see that how we can apply these tests to determine or to examine a given series is convergent or not. So we can understand from these tests that given a series to examine, what we need to do is we need to choose a second series. So if sigma un is given to you, we choose the second series sigma vn, which will be a known series, and we will actually choose the sigma vn either to be a geometric series or the p series, which we have already seen in the last session, and we know when they are convergent and when not. So if we know about this second series and we can compare the elements of the two series, then by the comparison test we can come to our conclusion. So let us see the examples. So the first one, examine the convergence of the series summation 1 by 3 to the power n plus 1. So here our given series un is 1 by 3 to the power n plus 1. Now it's obvious that 3 to the power n plus 1 is greater than 3 to the power n. So if we reciprocate, 1 by 3 to the power n plus 1 will be less than 1 by 3 to the power n. And this is nothing but the term of our given series un. And now let us call this as Vn. So from this relation, we can now see that un is less than Vn for every n. And what is this series sigma Vn, where your Vn is 1 by 3 to the power n? We can identify that. Yes, that is a geometric series with common ratio x equal to 1 by 3. And we know that geometric series is convergent when x lies between -1 to +1. Therefore, in this case, sigma Vn is convergent. So now see that we have two series sigma un and sigma Vn where un is less than Vn. And sigma Vn we have found to be convergent. So therefore by comparison test, sigma un is also convergent. Let's proceed to the next example. Examine the convergence of the series summation n by n square minus cos square n. So here our first series sigma un is such that un is n by n square minus cos square n. And now observe, of course, n square minus cos square n is less than n square. So if we reciprocate, 1 by n square minus cos square n will be greater than 1 by n square. Now if we multiply with the n on both sides, so n by n square minus cos square n will be greater than 1 by n. And this is nothing but our un, and this one only let us call as Vn. So now we have a relation that un is greater than Vn. Now what is the series sigma Vn? It's sigma 1 by n, which is nothing but the harmonic series. This also we have seen in the last session, and we know that this is a divergent series. So now by comparison test, what do we see? We see that the smaller series is divergent as un is greater than Vn, and therefore the bigger series or sigma un is also divergent. One more problem, let us see. Test the convergence of the series 1 plus 1 by 2 square plus 2 square by 3 cube plus 3 cube by 4 to the power 4 plus so on. So how can we represent un in this case? See that if we omit the first term, we call this as the first, this as the second, this as the third, then we can write un as n to the power n plus 1 to the power n plus 1, where n is going from 1 to 3. Now note that this will not affect our conclusion because we have seen a property that the convergence or divergence character of a series is not affected by addition or removal of a finite number of terms. Okay, now let us choose Vn as 1 by n and try to use the limit form now. So we form the ratio un by Vn and take the limit as n tends to infinity. So if we do so, it comes to be n to the power n plus 1 divided by n plus 1 to the power n plus 1, limit n tends to infinity. So this again can be written as 1 by 1 plus 1 by n to the power n plus 1. And we know that limit n tends to infinity, 1 plus 1 by n to the power n is a standard limit which is e. And here we will of course have another factor if we take this as n and another factor as 1 plus 1 by n. But as n tends to infinity, 1 by n tends to 0. So that part will become 1. So finally the value of the limit will be 1 by e, a non-zero finite number. And since we have chosen here Vn as 1 by n, so let us look into this series sigma Vn or sigma 1 by n. Now this is again nothing but the harmonic series which we know to be divergent. And therefore by the limit form of the comparison test, we see that the given series is also divergent. Okay, so with this example, we will close today's session. In the next session, we will take up another test of convergence, which is going to be D'Alembert's ratio test. So thank you and goodbye till then.